Okay, so I'm back. And so what we have is essentially is this kind of system of mx double dot plus kx of this system here. So this is something that you can now strongly relate back to your vibrations course. Okay, so that's the link. Let's go to the structural mechanics problem of saying we have a solid mass, solid body with a distributed mass. That's essentially what we have. What is the kinetic energy involved with that? So if you think about it, we have some body, like our potato. That's some control. That's some small volume inside that body. There's some displacements, field u, v, and w. So that's displacement x, y, and z. Then we also have u dot, v dot, w dot. That's our velocities in the x, y, and z directions. And so an additional parameter that comes into play is our density now. That plays a role. The density will play a role in terms of how this body will behave. So that's our mass distribution in the system. And so what's important is, if you want to think about, like we've spoken about, involving the finite element method in the dynamics in the finite element method, is we have to understand how does kinetic energy relate in the finite element method. How do we store kinetic energy? And for that we go back to our high school physics and say half mv squared. And so half mv squared in this kind of finite element kind of context is essentially half the integral over the volume for given density. So that will relate to me what is the mass in the system, and this u dot transpose u dot is essentially our velocity fields that are dotted on top of each other. That's essentially what we have, and this is a scalar that pops out. So our u dot vector, bold vector thing, is essentially our velocity in the x, y, and z direction. That's essentially these u dots, v dots, and w dots combined. And so what I end up with is essentially making sure I dot them so that yeah, I end up with kinetic energy here. So after I've dotted them out, I'll end up with a scalar. Okay, so that's it. So that's what I have. So these are three fields. So they are typically 3 by 1 vector, and if it's u transpose is 1 by 3, and then a 3 by 1, that's a 1 by 1. That's why we get up a scalar value there. Okay, that's it. How do we describe these velocity fields, u dot, v dot, and w dot? Well, let's think about how we did it with the displacement fields. We described them as nodal displacements with interpolation functions. So u equals nq. That was the way we described it. So the same with our velocities. We're just going to describe them as u dot equals to nq dot. So we're going to interpolate the velocities the same way, using the same shape functions as what we used to interpolate the displacements. That's essentially what we're doing here. Okay, and that, if I've done that, made the choice u dot is equal to nq dot, I can then go back to this and say, okay, let's go. Let's plug it in and see what happens. Okay, so if I plug that into that expression of our kinetic energy, which again is something back from high school physics, kinetic energy half mv squared, I get essentially this kind of the depiction here. I can pull out the q dots and the q dot transpose because they are our nodal values. They are constants. They are not something spatially that's been integrated about. All the spatial stuff is in here. So the rho n transpose n dv. This term here becomes my element mass matrix. So essentially, I can then this kinetic energy becomes a half q dot transpose mass matrix q dot. That's essentially my half mv squared. The same as my strain energy was half q transpose kq, which was my strain energy term. So now I've got the kinetic energy term and my potentially my strain energy term, which is essentially the strain energy in that system. And this gives me the formula then for computing using the finite element method a mass matrix that's consistent with the shape functions and the choice of interpolation for velocity. This is what I end up with. Okay, that's a beautiful discussion. Okay, or description that we have here. So me equals rho n transpose n dv. That's what we have. Okay, and so for those of you that want to go back to that sort of description of the Lagrangian kind of argument, we can get a description essentially for my potential energy, which is essentially half q transpose kq equal minus q transpose f. This is now for the forced case, but what this boils down to is kq equals to f if you take the derivative with respect to q. So that's really related to that what we saw way back in the beginning of the course when we did essentially the least squares fit, when we computed the weighted residual method. This is the energy approach for computing the weighted residual approach. Okay, but what it boils down to is shortly is to say we have a contribution from the strain energy side, which is the kx equals to f term, and there's a essentially the contribution from the acceleration side. And so I can really just go in and write down directly, almost say, if you want to do dynamics, we know from second year dynamics, we have mass times acceleration plus the elastic part equals to the forces that we act on the system. So I can almost directly just write this down from second year dynamics kind of knowledge. If I don't want to try and skip, if I want to skip this sort of potential energy argument, it's just to say this is the set of differential equations in time that I need to solve to be able to do dynamics in the structural finite element method. This KQ term takes care of essentially the elastic component. The F is the loads that are applied, and they can be a function of time or they can be constant. And this is essentially the acceleration side. And we know exactly what we mean with this M, because that's the element stiffness matrix. The global stiffness matrix is assembled from my element stiffness matrices. So it's the same way I assemble stiffness matrix. My mass matrix is essentially my global mass matrix is assembled from my elements mass matrix, and the assembly works exactly the same way as the assembly of this stiffness matrices. There is no different. It's also related to the global and the local degrees of freedom, and it gets assembled the same way. Okay, so we get then essentially assembled global stiffness matrix Q double dot plus K Q, which is essentially my global stiffness matrix. And so I can have sort of the forced vibration problem, or I can have the free vibration problem, where essentially say there's no force acting on the system. Okay, and so what will happen is essentially to say yeah, well, in terms of if I start off with a kind of for a steady state kind of condition, say this is my steady state solution to the problem, because remember there's no losses here, there's no damping matrix, so the system has no losses. So if you start off with saying, making a description of our steady state solution, say Q equals to U sine omega t, I can then essentially plug that in here, K times U times sine omega t. I can plug in the derivative. The first time derivative of this is essentially there's a cosine term. The second derivative of this is going to be a back to a sine term again. That's the second, and I can essentially plug that in, but I'll see that every time I take a derivative, there's an omega that will pop out. That's where that omega transpose comes from. And so this allows me then to sort of just have a way to derive a generalized eigenvalue problem, or to describe a generalized eigenvalue problem, which talks about sort of these kind of steady state conditions that we have. Okay, so and what they are is essentially what are these U modes that will vary as a function of time. So that's essentially what happens. So this is the generalized eigenvalue problem that I can solve, and allows me to get then eigenvectors and eigenvalues that talks about the vibration modes. So we've seen now what the eigenvectors of the stiffness matrix in isolation were. They were sort of deformation modes, and now that we solve the generalized eigenvalue problem, they become vibration modes. Beautiful, and this all relates back to exactly what you've done in the vibrations course. Okay. So let's look at element mass matrices and just understand that to some extent. Okay, so maybe, sorry, before I forget, one thing I just want to talk about is essentially when you look at the frequency omega squared is related to the Lagrange multiplier. So just the eigenvalue is essentially the vibration frequency squared. That's really what it boils down to. Okay, so that's essentially the vibration is given as radians per second. That's because we put it in the sine omega t kind of format. So that's a radians per second omega description. So it's not hertz direct. It's radians per second. And what you need to understand here is that's called the circular frequency. But the bottom line is that if you look at this omega squared and the lambda, the relationship between the Lagrange multipliers, these are things I want you to be able to be comfortable with. What does the eigenvectors mean in this case? What does the eigenvalues mean? That's important. And also, if I give you a stiffness matrix and I give you a mass matrix, what you'll see tomorrow as well is I want to be able to make sure that we're comfortable being able to compute